In earlier lectures, we discussed how voltage is generated in DC accelerators. As I mentioned, there are three types of DC accelerators. One is Cockcroft-Walton, Van de Graaff accelerator, tandem and peloton accelerators. In the case of Cockcroft-Walton, the voltage is generated by charging and discharging of capacitors. In the case of Van de Graaff accelerator and initially in tandem accelerators, the voltage was generated by charging the capacitor formed by the high voltage terminal and the high pressure vessel. In the case of peloton, however, the voltage is generated by a much better charging system, that is called inductive charging system. And although I have discussed this in last lecture, but I would like to give some more details of this inductive charging in this lecture also. So here is details of inductive charging in the case of pelotons. Basically, in the peloton accelerators, you can see that there is no contact of high voltage with the charging systems, and there is a pellet chain which consists of metallic pellets connected by the nylon insulators. So if you want to understand the principle of this inductive charging, you can see here, suppose there are two cylinders, metallic spheres A and B, and as they are metallic, so positive and negative charges are there on both of them, and they are neutral basically. Now you put a electrode here where you can later on apply the voltage. Now if you want to transfer positive charge, then you have to apply negative voltage on this inductive system. So what you do is that if you apply negative voltage on this inductor, then the charge is in this first sphere. The positive charge will go to this side and that will be collected here, and the negative charge will be repelled because of negative potential, and that will be generated, that will be collected here in this case. Now if you bring this second sphere, which was neutral earlier, close to the first one after applying the negative voltage and come in contact with them, then because they are metallic spheres, so this negative charge will be transferred to this. And the third stage is that if you remove this second sphere, metallic sphere, then these two spheres are separated. Positive charge on the first sphere will be uniformly distributed and the negative charge on the second end. So this will be the condition number 3. Now if you ground this second metallic sphere, which is the condition number 4, you can see that you can ground it, then this negative charge will go to the ground, but still negative voltage is applied to the inductive electrode. So this positive charge will remain on the first sphere and it will be uniformly distributed. However, there is no charge, negative charge on the second sphere is gone to the ground. Now this first sphere, which is representing this pellet chain, is moving with a speed, while the second sphere is stationary, and that is representing this pulley, which is grounded now. So what will happen, because this negative voltage is still on, when this is moving, the positive charge will remain here and the second sphere, the electrons have moved to the ground. So this first sphere will carry the positive charge and will be taken to the high voltage terminal. Now, as I explained in earlier lectures, that if you want to transfer this positive charge to the high voltage terminal, you have to put extra work, because now you are moving this charge against the high voltage, and therefore you have to put extra work, and that is done by this grounded pulley at the ground. So this positive charge goes to this, and this is how it will happen. This positive charge will go to the high voltage terminal, and then in the terminal there is a pickup pulley here, and above that there is a suppressor. So this pickup pulley will pick up some charge, positive charge, and it is connected to the second inductive inductor. Here you can see is inductor. So that means, as a consequence of that, the second inductor this inductor will get positively charged, slightly positively charged, and rest of the charge will go to this pulley here, and there is a suppressor which does not allow any sparking, because this second conductor, this suppressor, is connected to a pickup charge here, pickup pulley here, which is picking up negative charge which is coming in the second one. So there are two pickup pulleys, 1 and 2, and this is inductor and this is suppressor. So there is one more suppressor here, because this negative charge is coming down. Pellet chain comes in contact with the pulley, there will be sparking. So in order to suppress that, there is a suppressor here, and as a consequence of this, because of these two suppressors, one here in the high voltage and other one here, which is applied around 50 kV, and as a consequence of that, there is no sparking either at this place or this place due to charge movement. And then of course, when the charge goes to the terminal, is connected to this high voltage pulley, is connected to the high voltage terminal here, and the charge is transferred to this high voltage terminal. It is initially transferred to the inside surface of this, but as you know that this charge cannot remain inside a metallic conductor, so it appears outside. So this positive charge goes to the high voltage terminal here, and this high voltage terminal forms is a capacitor, because of this whole thing is put inside a pressure vessel which is grounded. In the case of so this forms a capacitor. So as per the formula, Q by C is equal to voltage. So voltage on this high voltage terminal will be raised. So this is the inductive charging. Now the advantage of this inductive charging is that first, there is no contact with the high voltage. Secondly, because we are using the metallic pellets, and therefore charge will be uniformly distributed, and therefore there will not be any non-uniformity of charge, and therefore charge will be uniformly transferred to the high voltage terminal, and this will lead to a better stability of the voltage. Third thing is that since it is metallic, pellets are metals, and therefore there is no formation of lints, etc., and therefore there is no high gradient form on the, as was the case in the belt charging. Here it is uniformly going, so much better stability can be achieved in the case of inductive charging, and that is what is done in the case of pelletons. And nowadays some of the tandem accelerators are also using this, and the difference between tandem and the peloton was because of charging only. So those tandems which are getting converted into pelotons, because of this inductive charging, their stability is also improved. These details are given in this NEC, because these pelotons are manufactured by NEC, National Electrostatic Corporation, USA, and you can see that some details are given here. So these are some of the details which I thought I should tell you about in slightly more details. Now today we are going to discuss lecture number 5, and which is voltage measurement and stabilization. Now in earlier lectures I have talked about how the voltage is generated in the case of tandem or Venn diagram, but this has to be measured, and this has to be measured accurately. The voltage defines the energy of the particle, and energy should be fixed. And therefore, the voltage also should be fixed, because voltage is charge times the energy charge times the voltage, charge state times the voltage into E, and this has to be done properly. And if there is any variation in the voltage, then it should be stabilized. So we have to incorporate a stabilization system also, which will correct any change. It will bring back the voltage to the original value if there is any change. So the circuit should be such that it stabilizes the voltage properly. So as I mentioned that in DC accelerators, which are Cockcroft-Walton, Venn diagram, tandem or pelotons, 3 processes are involved. First was voltage generation, and that in the case of Cockcroft-Walton, it was charging and discharging of the capacitors, and the voltage is generated by this formula. When Q is the charge transferred to the capacitor, that is high voltage. Then you have to measure the voltage, and in early days, main method which was used for measurement of voltage was generating voltmeter. In the beginning it was not very accurate, and therefore it was not really used to measure the voltages, and hence not used for the experiments. But later on, now with the advancement of technology, even better GVMs have been built, and they also are very accurate ones. Then the next thing is voltage stabilization. And as I said, that if there is any change, either the voltage is slightly increasing or decreasing, it should be correct back. So there should be some feedback system, and the system which uses feedback is called corona stabilization, or the generating voltmeter stabilization system. So it has to be corrected, and these are some of the systems which are, for example, this is Cockcroft-Walton, and this is shown the picture of that Cockcroft 1 million volt Cockcroft-Walton at the Tata Institute of Fundamental Research. This is Venn diagram, and this is 2 MeV tandem accelerator at BRC, which was, and then the peloton at TIFR. So these are some of the accelerating systems, accelerators, which are DC type, and in that one it is necessary that voltage is stabilized and energy is known for very accurately. Now, voltage measurements, as I said, was done earlier with generating voltmeter, or we call it GVM. And another method which can be used but depends on various parameters is using current through the resistor chain. You can see that the voltage gradient is established through a resistor chain, and suppose the total resistance is R, and I is the current. So in the last one you can put a current meter. So the I is the current total, then voltage can be calculated. Now the accuracy of this voltage will depend on how accurate are the resistances. So normally accuracy of the resistance is 5 to 10%, and therefore there will be error in the voltage of that order, and therefore we should have the very good quality resistances if you want very accurate voltages. Of course, once we know the voltage, then we can calculate the energy, which is E is equal to Q times V, where Q is the charge and V is the voltage. So let me just reiterate that what are the things involved. So voltage measurements and in calibration and stabilization is a fundamental problem for precise knowledge of nuclear energy constants, which are used for nuclear reaction studies or any experiment. So this is, so what you have to do, you cannot measure the voltage directly because they are very high voltage, several million volts, and therefore you have to calibrate it with respect to standard sources, and that calibration can have some errors. So, but you need precise knowledge of energy, and for that you have to know the precise knowledge of nuclear energy constants. The generating voltmeter has been used to measure the terminal voltage in DC accelerators for very long time. Initially it was used even to measure the energy, but as I said that may involve some errors, and therefore that voltage, nowadays the voltage measured using GBM is used only to get an idea about the voltage, plus to avoid the corona discharges and things like, or the breakdowns. So, but this has been used for very long time, and even today it is used very effectively, and therefore I will give little more details of that GBM, how it functions, and how accurately it can be used, and therefore I will like to talk about the working principle of this GBM, because that is popular even today, although some better methods are available, like you can calculate the energy through nuclear reactions, resonances, and threshold neutron experiments and things like that. But this is still very useful. It gives fairly accurate, although in the beginning there were more errors, but now with the advancement of technology, GBMs, good quality GBMs, giving accurate value of voltages have been are built, and therefore is fairly good voltage value can be taken from that, can be achieved. So in GBM, what happens? Static charge is induced on an insulated metal plate, or we call it veil, mounted on the outer vessel. As I said, that the outer vessel, together the high voltage terminal forms the capacitor. So this and outer vessel is grounded. So this GBM is mounted on the outer vessel, or we call it pressure vessel, and that is surrounding the high voltage terminal. The magnitude, now once you have high voltage here and there is a vein here, definitely there will be an electric field, and there will be a induced charge. So the magnitude of this induced charge is determined by the electric field established by the high voltage terminal on the vein. So this the last one is there are several veins, and last one is grounded. Just before that it is insulated, and voltage, the charge is collected on that, and that is rectified, and we measure the current, and then the voltage is measured through that. So high voltage terminal on the vein. So this is magnitude of induced charge on that one. It determines and charge induced depends on what is the electric field, and electric field depends on the voltage, so you get voltage value from this current which you are measuring due to charge collected on that vein. An insulated vein rotates at it. Now, how this is happening will be explained. So there is a insulated vein which rotates at a constant speed behind a grounded shield shaped so that the vein is covered during the half of its travel. So what you happen, suppose you take two veins, so this is fixed and this is rotating. So let's say these are slots. So when these slots are matching with the slot in the stationary one, then there will be an electric field seen by the another vein which is behind it, behind both of them. Now, since this is rotating, so as soon as it goes out of the phase, then there will not be any electric field seen by this plate. So that is what is happening. So this is rotating. So depending upon what is the speed, there will be a charge collected. So you can see here that there are 4 electrodes which are shown here. You can see here. First one is, this is the source or corresponding to this, and where we want to measure the voltage. So this is like high voltage terminal. Now you see, high voltage terminal is not touching any of them. So the GVM is a system which is not, none of the components are touching the high voltage. So this is a electrode, this is a vein or equivalent to high voltage source. Then there is a rotor, which is this one, and then there is a stator, and there are fixed electrodes. So you can see here, there is a rotor, a stator, and this is a phase. So this actually opening is almost very close to it, but it's not touching the shaft. So there is a shaft here, is passing through this, and it is rotating this rotor. It's rotating this rotor, and this is by a synchronous motor, because speed has to be fixed and it has to match, because it has to go out. It has to be in phase. Rotor has to be in phase with the stator and out of phase. So in the phase means that it is electric field is seen, and when it is out of phase, it's blocked, and therefore there will not be electric. So these are metallic disc sort of thing with slots. So this is the high voltage source. There is no slot here. This has slots. These are identical slots, and this is rotating, and this is fixed, and this is a fixed electrode, which is which we mount on the. Now, one good part of it is that there is no physical contact between high voltage and rest of the circuit. That's the beauty of it. So it's like induction, and synchronous motor is used, shaft holding rotor disc only. Now, how the voltage measurement is done. Now let us try to analyze it. So we know that Q is equal to CV. That means charge induced on that is proportional to the voltage, because the electric field is proportional to the voltage, distance, etc. And therefore charge induced on the plate or the disc is proportional to the voltage which you want to measure. So charge is the Q is the charge is stored in a capacitor of capacitance C, and V is the voltage developed across that high voltage term. Now, as I said that rotor is rotating, so that means the C or the capacitance value will keep changing, and since it is rotated by a synchronous motor, so the C can be assumed to be varying in a certain manner. So there will be fixed value plus there will be, let's say, sinusoidal component added to this. So C is varying with time, then the current passing through the capacitor is given by I is equal to dq by dt, and Q is nothing but C into V, and therefore it becomes V into dC by dt plus C into dV by dt. So now, so this is the current which will flow based on these two values. Now, in the case of DC accelerator, the voltage has to be fixed. And the variation is very little, and ideally you would like to see that the voltage is constant. So if the voltage is constant, then dV by dt, the time variation of this, is equal to 0. So for the sake of analysis, we can put dV by dt is equal to 0. Although it will not be 0, it will have a very small number because that is what we want to stabilize it. So, but to the first approximation, to the first order, it will be dV by dt will be 0. Now let us say if C varies as C naught, that is a constant value, plus Cm sin omega t. And here this variation, this addition to this is because it's rotating and is both whenever slots are matching, then there will be a variation in it. So that means C varies at like this. Now that if this is how this capacitance is varying, then the current can be written as current is equal to V into d by dt of C naught plus Cm sin omega t. Now Cm is the peak value of this, and when you differentiate it, since C naught is constant, we are taking that's the constant value, and over and above there is a variation, and that variation is shown by this. So that means d by dt of this C naught will be 0, and therefore the I will be equal to V into Cm, which is a maximum value of that, into omega cos omega t, and this you can write as Im, that is a maximum. So this becomes Im, maximum current, cos omega t. So this becomes the Im, that is the maximum value. This is a peak current, and omega is the angular frequency in radian per second, and it is given by here, and n is the RPM of the motor, synchronous motor, which we are using. Now if you see, then the RMS current which we measure is nothing but Im divided by root 2, and therefore Im will be root 2 times I RMS, and that is this Im is shown to be here. So this is Im. So that means V, the voltage which you are trying to measure, is nothing but root 2 times I RMS into Cm into omega. Or you can say that here the voltage is proportional to I RMS. And that RMS value of that voltage we are measuring through a meter or something. But once it is proportional, that means, see, ultimately what you are doing is you are measuring the current, and which is a root mean square value of the current, and that is proportional to the, that is V is proportional to, that means you have to calibrate it. You have to calibrate these values with known sources. And these known sources will depend, this calibration constant will depend on several parameters like geometry of the voltage source and etc., many more parameters, and hence the proportionality constant may not be very accurate. And you cannot, so normally when you are calibrating it, you normally calibrate at lower voltages and try to extrapolate it to the high voltage, because ultimately you are measuring the high voltages. and the constant obtained at a low voltage may not be very accurate or will not be usable at high voltages. So this has to be taken into account. The alternating electrostatic voltage induced in the vein is amplified and rectified. Its magnitude is a measure of the terminal potential, but calibration with known sources is required, and that is what may involve some errors. So in this method, geometry plays a very important role. The geometry of the system limits the precision of the calibration constant from the calculation of the capacitance. So there may be some error in the calculation of the capacitance itself, because geometry of the high voltage terminal may be slightly different, or may you have to, and the electric field also. What I mean is that suppose the geometry is let's say normally, as I showed, that high voltage terminally, let's say like this, is a cylinder, and here we are using this GVM, and the electric field from this, let's say this is a very small portion now, which is used for this taking the charge. Then the electric field coming from different places will be different, and therefore this may add to some errors. Also, if the geometry, in some cases it may be cylindric hemisphere, or in some cases it may be cylinders, or even combination of that, and therefore you have to be very careful when you are using those constants which are used for measuring the voltage. So geometry has to be properly defined, and finding the calculations of capacitance and constants. And here the most serious limitation is the distortion of electric fields, as I explained just now, due to corona discharge from the terminal. See, we are handling now high voltages, so there will always be some corona formation. So once there is a corona formation, there will be distortion in the electric field, and this electric field may vary slightly, and that electric field is responsible for inducing the charge. So once there is a variation or in the electric field itself, then there will be a variation in the charge induced and hence the current which we are measuring, and so this may add to some errors. Voltage scale is usually calibrated against some other standard potentials, normally at lower voltages. This I have repeatedly said, that your calibrations are normally done at lower voltages, and you are trying to extrapolate it to what? Say, for example, suppose you take a DC accelerator with 10 million volts or 20 million volts. Then you can't measure this very accurately. You can measure there will be generating voltmeter, because their distance also will be large, but there will be some errors involved in it. So we have to be very, very careful, and therefore some other good method has to be used to find the energies of the particle which we are going to use in the experiments.